In this section, we're going to look a little bit more at the arithmetic sequences that we first saw in the previous section. Again, it looks the same as arithmetic, but in this context, it's pronounced arithmetic. So arithmetic sequences have a common difference. So if you subtract any term by the previous term, any term by the previous term, this term by the previous term, they'll all have a common answer. They'll have the same answer. So here that's 3, or again, we can see if we look at the pattern is going to look like adding or subtracting every time. So here we've got a pattern of +3, +3, +3, every time. So that's what an arithmetic sequence looks like. Now, what that means, though, is that means they're going to behave like linear functions, because that means this +3, that's like a constant rate of change. The rate of change between terms is the same. And so well, a constant rate of change, that's a constant slope. That's a linear function. So if we looked at these values, so we have them here as terms in a sequence, we could also look at them as xy pairs. If we had the number term as the x, and then the value of the term as the y. Well, if we look at this as a function now, we're going up 3 for every step forward of one term, up 3 for every step forward of one term, up 3 for every step forward of one term. We've got this constant rate of change, this constant slope, so it's a linear function. So in sequence world, we call it d, the common difference is 3. In function world, we would call that the slope, the m, being 3. 3 over 1, of course, change in y over change in x. 3 over 1 is just 3. Okay. So now what about writing a formula or a function for this? Well, in the previous section, it was a little bit more kind of, trial and error, just think about it kind of thing. One thing we looked at was if we're adding over and over again, well, repeated addition turns into multiplication. And so we would say if we're adding 3 over and over again, we have to have some sort of 3 times n. So we've got that, and then we just sort of kind of looked at it and checked it to try to kind of fix it and make it work. So right now, if I look at the first term, right now my first term would be 3. I want it to be 5, so I'm off by 2. If I plug in 2, 3 times 2 is 6. I want it to be 8, so I'm off by 2. I just need a +2 in there to kind of fix it and make it work. Well, what that means here is that this function then is 3x plus 2. Now, if we think about it in function world, though, we wouldn't have had to kind of do so much kind of guesswork or trial and error. In function world, we know we have the formula for the equation of a line, right? That we've got y equals mx plus b. And we know our slope was 3, our constant rate of change was 3, so that part's easy. And then what about the b? If we were thinking about this like an equation of a line, instead of having to just kind of guess and check or figure out what was missing, in function world, when we're thinking about the equation of a line, we know exactly what this number should be, what this b is. It's the y-intercept when x is 0, right? To figure out this 2, you could look at the graph, figure out what that point is, or you could go back and figure out, all right, well, when x is 0, if we continue this pattern here, well, if it's +3, +3, +3 this direction, going backwards, it's -3, -3, -3, -3, or think about what would you add 3 to get 5, you get that, and so either one of these things here could have told us what that b is. Well, why don't we leverage that when we're in sequence world? Right? Even though these are kind of different worlds, different ways of looking at this, the math still works. All of the same math still applies. So if I want to figure out what this 2 is supposed to be right here, I could figure out, okay, sequences are always supposed to start with a first term. It doesn't make sense to have a 1.5 term or a -2th term, or actually even a 0th term. But what if I did have a 0th term? What if there was a term before this? What if I could have a t sub 0? What would it be? Well, think about this pattern. What number has to be here to make this pattern work? And it has to be 2. So if I figure out what that 0th term would be, that's going to be this right here. If I think about this as mx plus b, I can use a common difference as the average or the constant rate of change as my slope, and then the 0th term as my b. And I can figure out this formula very easily. Okay. Now, if you don't like this, if you don't like mixing sequence world and function world, there will be another way to do it that we'll talk about in a minute. But for those of us that makes a lot of sense, let's try this right here. All right. So first of all, let's make sure we see this is arithmetic. Let's make sure we see the pattern. This one's going down 9 every time. We're doing minus 9 every time. So this is arithmetic. So the negative 9, that would be our d. If we were in function world, we would call it m. We would call it the slope, the constant rate of change, right? So to write my explicit formula, so I want to say t sub n equals, I can think about it like I want to do y equals mx plus b. My m, my slope, my constant rate of change would be this negative 9. And then instead of saying x, my input isn't x anymore. My input is n. And what about this b? What about the initial value? What about the y-intercept? What about when x is 0? Here it would be when n is 0. It would be a 0th term. So if we could go backwards, if we could figure out what the 0th term would be, what would that be? If we subtract 9 this direction, then going backwards, we have to add 9. Going this direction, add 9. Negative 5 plus 9 is 4. 4 plus 9 is 13. 13 plus 9 is 22. All right, so this 0th term would be 22, so that would be my b. So that means my formula right here would be negative 9n plus 22. There we go, that's it. You can just think about this like mx plus b. Now, if you don't like that, mixing those two worlds, and this, that won't be what you'll see in, most textbooks or other videos about this or anything like that. What they'll do in most other places is they'll say, well, sequences don't have a 0th term. They don't have the b. And so let's try to have a formula where we only use what's actually in the sequence. And so they'll come up with a formula that's based on t sub 1, on the first term. And so here's the idea that they use. All right. So what we're going to do is we're going to look at how do we get any of these terms from the first term. So what we look at is, okay, from the first term to the second term, you just add the 3 ones. Okay. What if you wanted to go from the first to the third term? Well, there'd be the plus 3 here, and then there'd be another plus 3. There'd be 2 plus 3s. Well, repeated addition is multiplication. That's 3 times 2. To get the third term from the first term, you add 2 3s. What about to get the fourth term from the first term? Well, that's going to be 3 steps forward, right? You're going to do plus 3, plus 3, plus 3. From the first term to the fourth term is 3 steps forward. You'd add 3 3 times. You're adding 3 times 3. A repeated addition is multiplication. The fourth one is the first one plus 3 3s. Okay, well, let's keep going. Let's think about a couple more and then try to generalize this. Well, how many steps is it to the fifth one? The fourth one was 3 steps, so then to get to the fifth one, you'd have one more step. It'd be 4 steps. To get to the fifth one, you do plus 3, plus 3, plus 3, plus 3, plus 3 4 times. 3 times 4. How about the 10th one? From the first to the 10th is 9 steps forward, 9 steps of 3. Okay, so now is when we need to generalize this, try to do this in terms of variables. What about t sub n? What about the nth term? Well, do you notice the pattern here? The fourth term, we needed 3 steps. The fifth term, we needed 4 steps. The 10th term, we needed 9 steps. It was always 1 less, right? So the nth term, we need n minus 1 steps. So the formula that you'll see for an explicit formula for an arithmetic sequence, if you watch other videos about how to do this, the way that they'll typically do it is they'll take the first term, and then this 3, what was d, right, was our pattern, our common difference. So they'll take the first term, and they'll do plus d times n minus 1. And this is what they'll use to find the explicit formula for an arithmetic sequence. Okay, so for this problem right here, what they would do is they would say t sub n equals, and then they wouldn't have this 22 here. Remember that 22 doesn't actually exist. The sequence starts at 13. So it would say the first term was 13, and then they would say the d was -9, and then n minus 1, n is your variable, right? N is your input variable, so you just leave that one as n. You fill in numbers for those two and leave n as a variable. All right. Now, do make sure if you want to use this formula, if you like this way better, make sure that you simplify. I'm not going to give you full credit for this. I want a simplified formula. And so what you have to do is be careful. Don't let that addition call out to you too much and distract you. You're not allowed to do the addition first, right? We've got to multiply, distribute first. So we're going to have 13, and it's going to be minus 9n, and then plus 9. And so then we'd have some like terms. So again, this is a different way to do it here. So what we'd have here, this t sub n would equal, well, we'd have the -9n right there, and then 13 plus 9. Look at that, same answer. It's like math works. Math works. Okay. So it's totally up to you, whichever way you like better. Personally, I don't like, knowing extra formulas or memorizing extra formulas, and, look at how much extra work this was right here. Really, because everything that I wrote in red, what was extra, like we didn't have to write this stuff in red. This is just kind of showing you the thought process. So really, we could have written this formula without any work, if you understand this y equals mx plus b idea. Okay. Or if you like this formula, if you don't want to mix sequence and function worlds, then go ahead and use that formula, and that's perfectly fine. Whichever way you like, it's totally up to you. You just want to make sure that you know how to write a simplified explicit formula. All right. All right. So what if we want a specific term? What if we want a sub 41? Okay. Well, we always have to start by identifying the pattern. That's always going to be the important first step, is what is the pattern in the sequence. So this one's going +8, +8, and +8. All right. And so one way to do it would be just to think about the steps idea. Right? You could say, what if we just pick up from where we left off right here? Right? What if we say we're going to do 27, and then we're going to add some 8s? Well, where, I mean, you could keep listing it out, right? You could say like 35, 43, like, if you had time and didn't know how else to do it, you could just keep writing out the entire list until you got there, right? You would just be adding 8, adding 8, adding 8, adding 8. Well, how many times would you have to add 8? Right? Well, this was the fourth term, right? So we've got the fourth term right here. Well, how many steps is it from the fourth term to the 41st term? That's 37 steps. So there'd be 37 eights. We've got 37 steps that we need to get to the 41st term. All right. And you could use your calculator if you needed to for that. That would be 323. Probably want a calculator. We'd probably give you your calculator a problem like that. The arithmetic's not too bad to do by hand, but why not use a calculator? All right, so that's one way to do it. Another way to do it would be to use this formula right here. You could say, all right, we're going to do t sub 41. So that's going to be the first term, which was 3. And then our d was 8. And then we want n minus 1 right here. So when we say t sub 41, we put the 41 where the n went. So our 41 is n right now. So we'd have 41 minus 1. And so we're using that formula right there. We're doing t sub n equals t sub 1. Notice I kind of mix the a's and the t's sometimes. So we've got different letters. The Algebra 2 textbook tends to use t sub n, t sub 1. Pre-cal and often calculus uses the a sub n. So I'll kind of go back and forth right here. Probably since this problem started out as a, I probably should have done everything as a. But you get the idea. The letter's not super important, kind of like doing f of x or g of x. Just different names for it. So we've got 3 plus 8 times 40. That one's a little bit easier to do without a calculator. 320 plus 3, 323. Okay. So a couple different ways to think about that. Yeah, you could have also, if you like the y equals mx plus b way, you could have used that. You could have said a sub n, and then your m was 8, so 8n, kind of like 8x, and then figure out what your b would be. Take a step backwards here, and that would have been -5. And so if you've got this explicit formula right here, you could just plug in 41. You could say that means a sub 41 equals 8 times 41 minus 5, 328 minus 5, 323. Same answer again. Math works. No matter which way you do it, you get the same answer. Okay. All right, and so notice we've been using a lot of explicit formulas here. We've been looking at these formulas. These are called the explicit formula. There's another kind of formula for sequences that you'll run into sometimes called the recursive formula. So the explicit formula is going to be better, where we're not going to like the recursive as much. The recursive is used more for computers. Explicit is nice. Explicit, if I've got the explicit formula, if I want the 41st term, I just plug in 41. If I wanted the 105th term, I could just plug in 105. The explicit formula is really nice, is really useful. Okay. The recursive formula would not be quite as useful. Again, it's used more in computer programming. And so here's the idea here. We're going to have some sort of a sub n kind of thing on both sides of this formula, on both sides of this equation. And we have to give you one of the terms. Because here's what this says. This says that the next term is whatever term you're looking at, plus 3. Right? The next term equals the current term you've got, plus 3. So that means you have to have a current term. You have to have a starting place. If I don't tell you this, then you don't know what the sequence is. You have to have somewhere to start with, and then this formula tells you what the next term is. Okay. Let me show you what I mean here. Okay. So let's say that we made n equals 1 for this formula here. If n equals 1, then when I plug this in, this n plus 1 becomes 2 right here. I get a sub 2 on the left side, and then this right here is a sub 1 plus 3. So this formula right now, if I make n be 1, tells me that a sub 2 is a sub 1 plus 3. Right? The next term is the current term plus 3. So this term started at 5, and then to find the next one, I just add 3. Okay. I take this 5 plus 3, and I get 8. Okay, well, now I want to figure out the next one. Let's figure out what the next term is there. Right, well, now I can do this again. Now let's make the 8, instead of it being the next term, let's make it the current term. Now I can figure out that the third term is the second term plus 3. If I make n equals 2 in this formula, then I'll have a sub 3 is a sub 2 plus 3. So now to find the third term, I can take the second term and add 3. So I get 11 right here. Well, now I want to find the next one. All right, notice with this formula, I can't just jump to the 10th term. If I want to find the 10th term, then I need to know what? If I want to find the 10th term for this with this formula, I would need to know the 9th term. If I wanted to find the 25th term, I would need to know the 24th term. So again, this is mainly used in computer programming. They have something called like a for loop, where you can just kind of keep looping things over and over and over again using recursive formulas. And you can build things out really quickly with this. For us, not quite as useful. But now if I want the fourth term here, the fourth term is the third term plus 3. So basically, what this is telling me is that this plus 3 is the pattern. To go from any term to the next term, I just add 3. So my pattern is plus 3, plus 3, plus 3 over and over again. All right, it's called a recursive formula. It tells you how to get one term from the previous term. Right, and it can look different ways. So again, the a or the t, that doesn't matter, just like f of x, g of x. Notice sometimes we might also use k instead of n. Just letters. There's not as quite as much of an agreement on the convention like there is like with f of x. Everybody uses f of x for their first function. And we've also got a different way to do a recursive formula here. But it's going to be the same idea. This -5 is going to be the pattern. What this one says is to get any term, take the previous term and subtract 5. All right. Any term equals the previous term minus 5. This one had a +1 in it, so you can kind of think about it like the next term. And then a sub n was the current term. Here we've got t sub k, we'll just call that any term, a sub n, t sub n, t sub k, whatever it is, any term, a general term, and then t sub k minus 1. Well, that's the previous term. So this one starts out as 15, and then you want a sub 2. Well, to find a sub 2, you take a sub 1 and you subtract 5. So take a sub 1 and subtract 5, and we get 10. Well, now you want t sub 3. Well, to find t sub 3, take t sub 2 and subtract 5. So again, recursive, you just have to recognize, whichever way it's expressed, just recognize that this extra part right here is the pattern. So we just keep subtracting 5, and that's our sequence. Okay. So why don't you take a look at this next problem right here. This one has a recursive formula there, and see if you can write those first 4 terms, and then see if you can find an explicit formula for this sequence right here. And then also take a look at this next problem right here, where we're going to get a formula for that in a minute, but I want you to see if you have any ideas about a quick way to do this without typing all 100 numbers in your calculator. There's actually a great story of where the formula came from, and someone who had this here. I guess they had like a substitute teacher in their class that was just trying to kind of keep them busy. So they told the whole class, all the students, why don't you just sit there and add up all the numbers from 1 to 100? That'll keep you busy and out of my hair for a little while. But one of the students, a famous mathematician named Gauss, came up with a really slick, quick way to do that easily. And we're going to look at that idea and turn it into a nice formula. So go ahead and do this problem, and then just take a look at this for a minute. See if you have any ideas how we might be able to simplify that problem. Go ahead and give this a try. All right, so there's the answers for this example here. Again, recursive just shows you the pattern. The pattern here was +4 every time. So to get to the next term, just keep adding 4. This right here is optional, right? If you wanted to use that formula, you could, or you could have just thought about y equals mx plus b. The 4 was your m. If you take a step backwards, your 0th term was your b right there. Either way, up to you. All right, so how about this? How about trying to add up those 100 numbers without typing them all in? All right, so here's the brilliant idea that Gauss came up with to try to do this task that his substitute teacher gave him to try to keep him busy. He paired up the numbers. He said, if I pair up these numbers right here, pair up 3 and 98, pair up 2 and 99, pair up 1 and 100, and then in the middle you'd have a bunch of other pairs as well. All of those pairs add up to the same thing: 101, 101, and 101. Okay, so I've got, if I want to add up all these numbers, I can just add up a bunch of 101s. Well, how many 101s would you have to add up? Well, how many pairs are there? If there's 100 total numbers and they each get paired up, well, there's 2 numbers in each pair, that's 50 pairs. So we've got 50 pairs of 101. So that's 50 times 101, 5,050. A lot quicker than doing a whole bunch of addition, right? Really cool idea. And what we can do is we can generalize this for any arithmetic series. Remember, it's called a series if there's pluses instead of commas. If it's just numbers sitting there in a list, it's called a sequence with commas. When we add them all up, we call it a series. Okay. All right. So, well, the pairs right here, the number of pairs. Well, how do we figure out the number of pairs? We have said that well, there was 100 numbers, so we did 100 divided by 2. That's how we figured out the number of pairs. We took the number of numbers, and we divided by 2. That was the number of pairs. And then where did this 101 came from? That came from how much a pair added up to, right? Well, the easiest thing would be to find one pair would just be to take the first and the last number, right? That 101 was 1 plus 100. It was the first number plus the last number. All right, so let's try to generalize that. So let's try to find the sum of the first n terms of an arithmetic series. We call that S sub n. Right? So capital S has a special meaning. You know, for a sequence, you could use A, you could use T, you could use different things. When we use a capital S, that means we're summing up a bunch of numbers. All right, so the number of numbers is the number of terms. So we've got n terms. So we're going to have n over 2 right there. That's the first part. And then the first plus the last number. Well, the first number is the first term. We call that a sub 1 or t sub 1, depending on what you want to call it. Okay? And then the last number, well, the last number here, this was a sub 100. It was the 100th term. That number down there matches the number of numbers. It matches n. And so what we do is we call this a sub n or t sub n. Okay? So what we just did S100 by doing 100 divided by 2 times a sub 1 plus a sub 100. All right, let's try this formula out. All right, so we want to find the sum of the first 40 terms of this. Now, first of all, always make sure that it is actually arithmetic. This only works if it's an arithmetic series, right? Well, it is. Our pattern right here is we're going plus 5, and plus 5, right? So it is arithmetic. So that looks good. All right, so for this formula, we need 3 things. All right, we need n. Well, that's this 40 right here. The number of numbers, the number of terms. So we know n. We need a sub 1. Well, that's the first term. That's easy. 2 out of 3 down. Easy. How about a sub n? Right? A sub n, remember, is the last number. So that's going to be the 40th number. So in this formula, where it says a sub n, what we want is a sub 40. We don't have that yet, right? So we got to figure it out. Right? That's just like this problem that we did back here, right? Back here we wanted a sub 41. Now we're just going to find a sub 40, right? If we had a sequence and we wanted to find a particular term, there was a whole bunch of ways to figure it out, right? So whichever one of those ways that you liked better, I'll do the one that kind of matches the formula, but it also kind of makes sense if we're thinking about this here. If we start with the first term, then we're adding 5 a bunch of times. How many times do we have to add 5 to go from the first term to the 40th term? How many steps is that? 39 steps. Okay, that's also the formula we had, right? A sub 1 plus d times n minus 1. All right, and so again, you can use your calculator for that if you like. 150 plus 45, 195 should be 197. All right, so then we've got all the pieces for the formula that we need. So we can say S sub 40 is 40 divided by 2. Again, this means the sum of the first 40 numbers. N was 40, a sub 1 was 2, and then a sub n, a sub 40, the last number, 197. All right, and you can type that in your calculator as is if you like, or you can simplify that a little bit first if we like. At that point, you probably want a calculator. This ends up being 3,980. All right. What about sigma notation? Do you remember sigma notation? Right? So sigma notation does mean to add up. It does mean to find a sum, right? And then how about, do we know if this is an arithmetic series? Well, you could start listing out numbers if you wanted. You could plug in 1, plug in 2, plug in 3, plug in 4, and so on, and see that it does have the arithmetic pattern. Or notice this right here. This looks like mx plus b. That means it is arithmetic. Remember, arithmetic sequences or series are like linear functions. So if the formula, remember this was the formula for the terms, looks like mx plus b, it has to be arithmetic. Okay, so we know it's arithmetic. How about, do we know the number of terms? Well, it starts at 1 and goes to 21. So that means there's 21 terms. That means n equals 21 here. Okay, so we've got n. How about a sub 1? We actually don't know a sub 1 yet. A sub 1, we have to use the formula to figure it out. Let's plug in 1, negative 2 times 1 plus 52, negative 2 plus 52, that's 50. And then a sub n, that's a sub 21 here. We don't know that one yet either, but we've got a nice formula for it. That's the nice thing about sigma notation. It gives you the explicit formula. So we've got negative 2 times 21 plus 52, negative 42 plus 52, that's 10. So then we got all the pieces we need. Let's fill all these things in here. So we've got s sub 21. The sum of those 21 terms is 21 divided by 2 times 50 plus 10. All right. And you can type that in as is in your calculator if you like, or if you're trying to do it without a calculator here, the over 2 can actually shift over to the other part. Dividing by 2 is the same thing as multiplying by half. You can multiply whichever part you want. So you can actually do, so this 50 plus 10, that's 60, right? You can put the over 2 on the 60. And so then this is 21 times 30, which would be a whole lot easier to do, right? 21 times 3 is 63, add the 0, and we get 630 for our sum.